I wish I could move this stuff out of the way though. There we go. Recording good? Okay. So this week I'll be talking about the MAGVIT paper. And so this is a paper that's all about video generation. And so typically I start with the slides and I go through and I explain, but I think since it's video stuff, I'm just going to show you some videos first, and then we can go back and say, okay, what is the model actually doing? Because it's more interesting to look at the videos than look at some slides. So this MAGVIT paper is just all focused on how do we generate videos realistically and efficiently. So images, we've gotten really good at generating them. So you do diffusion or flow matching, or like there's all these different techniques now to generate images. But then when you scale up to video, it becomes much harder because if you were generating one image before, now you're generating 24 images just to make 1 second a tiny little GIF or animation or something. So the scale of this becomes insane because you have video is just an extra axis on top of your images. Um, this paper is very cool because it can do a lot of different things simultaneously. So we can look at all of these different kinds of things that the model can do. So one of the things is you can start with just a single image and then just say predict the next few frames of it or something like that. So this is this frame prediction task. You get an image and then it just kind of predicts what's the next few frames going to be. Or you can do frame interpolation. So they give like a beginning frame and an ending frame, and then it says fill in the middle. So what was in between this whole scene? So they've got like, here's sundown, and then here's further before or further after, and then they say guess all of the frames that were in between, like predict this sunset, basically. And then they also can do central outpainting, so you get this crop in between and say like basically expand the video out. Or you can do it in a more structured way, saying like expand it horizontally or vertically. And they can even like uh, put a hole inside of it and move it around and say, just predict anything. Just basically fill in the blanks anywhere in the video. Um, and this is the first version of this paper. So this is MAGVIT, and there's a MAGVIT 2, and now there's been a bunch of like follow-on work after it. But I figured I would start with the first paper because it gives a good like framework for just how to do this in general. Um, so with that, I'll go back to the actual slides now that you understand, like this is kind of what the model's trying to do. Um, so, like I mentioned, we've gotten good at generating images, but now doing it with videos is very hard. So, if you just wanted to generate 24 frames, that's 24 times the amount of work of just generating one image. And then one of the big difficulties with that is you need continuity between frames. You can't just say generate one image and then generate another image because their relationship between each other is going to be very weak. So, humans are very good at looking at image video and saying this one and this one were not quite correct. So if something even shifts like a couple pixels, it's very apparent to our vision because we take a lot of focus on that. So there's a bunch of popular techniques and there's different ways to do video. So people have done diffusion and GANs and flow matching. And so the big thing here is you want high quality, you want like high fidelity video that looks realistic and has all of the details right. But then you also want low memory and compute usage. So it's really difficult to fit an entire, I don't know, 5 minute video into your GPU's memory. You just can't do it. So you have to kind of find some optimizations in some ways to be able to handle that. And then the other thing is speed. So a lot of these different approaches, if it takes an hour to generate a 3 second video, that's not very interesting. And it just costs way too much in terms of compute. So this MAGVIT model is really made up of two different stages. So the first stage is just a fancy autoencoder, and I'll talk about that more in later slides. But the idea is basically we have this big high resolution video, and then we want to compress it down as much as we possibly can, and then decompress it. And so we train a model to do this, and then we can take that middle section where it's very heavily compressed, and then we can do predictions in that space instead of the full space. And that saves us a whole bunch of memory, and it helps us create higher fidelity output and a bunch of positive properties out of that. And then the second step is the transformer. And so this is the part where we say, now we have this tiny little condensed representation, just guess the next frame or guess the panel to the right of it or panel to the left of it or guess the frames in between. And so you can train a transformer model that learns the sequences on that really compressed bottleneck area. And that's much better than saying I'm going to train a transformer on the whole thing. So doing it in 2 stages gets it to be much more efficient and much faster, and we'll look at all of the factors on later slides. So the stage 1 of this 3D vector quantized autoencoder, the idea here is you want a very, very compressed representation in the middle, and they want it even beyond just like your regular neural network is going to have a bunch of floats in between saying like this is the representation of this data. We want it even smaller than that. We want it discrete tokens. So you have some like top left portion of the image and you say this 16 by 16 image is just represented by a single number, for example. So you have a certain vocabulary, and that's kind of your building block of all of the images that you can generate. And so they compress it super, super heavily. So the variant that they trained is making it 8 times smaller on height, 8 times smaller on width, and then 4 times smaller on the like time axes, the frames. So just looking at that alone, that's 256 times compression. So if you had a 128 by 128 video and 64 frames, you're then going down to much, much smaller on every axis. And then you just have this like small sequence of tokens that represents the whole video. And so they're able to compress this so heavily because in previous attempts, a lot of people have done just purely image autoencoders. And so it represents a single image and then it compresses it very heavily. But there's kind of a limit on how much you can compress it and then get good results back out. If you make it too small, then you can't get the original image or something that looks like it back out. And a big advantage of videos is often the frames are very related. So if you have a video, frame 1 and frame 2 and 3 and 4 are probably all going to have very similar colors and distribution and everything. And so this is kind of one of the first works that did a 3D version of this autoencoder. Previously, most people had stuck with 2D, and this is kind of the jump from JPEG to MP4. So the MP4 is able to compress things so much stronger because it's looking at that time axis in a different way, and it knows that the sequence is all related. Yeah.
So just a quick comment I want to make is sometimes we talk about like low rank approximations, and in the book club we're talking about linear algebra and subspaces. So if you were to do a down projection, then that could only give you a linear reduced dimensionality representation of this whatever like patch from the frame over time. But because they're using vector quantization, which like we could spend the whole time talking about that, but basically it's using a code book. If you have 1024 entries in your code book, they do not need to be linearly related, like if you had just a matrix that you were using to multiply to down project it. So I just wanted to mention so that using vector quantization gives you much better nonlinearity than if you were just using a matrix multiply. So that's like kind of a theme you see in some of these models. So I think the matrix multiply might be a little cheaper and easier, but this one's better when you need nonlinear.
Yeah. Yeah. Um, so we saw some of the videos beforehand, but this is looking at just the first stage of this. So this what it's doing is it's showing this top row is the real videos, and then the bottom row is the reconstructed. So what this is showing is it took the video input and then it encoded it and then it decoded it, and we see how much information it actually lost. And if we look at these actual videos, you see that it looks pretty good given how much it compressed it. So it made it so compressed on the height and width and frames and the quantization and all of this stuff, and it's still able to give us an output that looks very similar to what it originally looked like. So this makes it a very good condensed representation for us to look at. And then the second piece of this is the mask token modeling. So now we've taken the video and we've turned it into tokens, and we can do whatever we want with these tokens. We can guess future ones, we can guess the ones around it, we can guess the ones in between. And so now that it's in token form, we can do it like we do with language, where we say, give it a transformer and then put the tokens in and have it do whatever you want. And we have all of these innovations in terms of transformers and their ability to model sequences, and we can say, okay, apply this to video now. And so this second stage is saying you have these tokens, train it in all of these different ways, and then it will get good at predicting all kinds of different things, and it understands the relationship between, oh, if this pixel over here was red, then the one next to it is probably also red, and things like that. So here's the full pipeline. They laid it out a little bit confusing in my opinion, but we start over here with the raw video. And then what this does is this is the encoder and it reduces it down to tokens. So imagine this is like a 128 by 128 by 64 frames of the video. And then it goes through the encoder. And then this might be 16 by 16. Um, and then we have a certain reduction on the frames too. So it might be 16 by 16 by 4 or something like that. And then we have this super condensed representation, and then we can do a bunch of different stuff with this. So here's all the different modes that the model can be in, where we can say, okay, give it only the first frame and guess the next few, or punch a hole in the middle and guess the ones around it, or just move a box around and say fill in wherever that box is. So this is just a diagram showing all of the different things that you can do once you have it in this token form. And so you have it in the tokens, and then you say, pass it to a transformer, and then predict given a little prompt telling it what to do. So you might have a prompt saying, guess the next frame. You might have a prompt saying, fill in the blank. There's a bunch of different things that you can do there. And so you train this transformer to do all of those different tasks simultaneously. So then when you actually want to do inference, there's a little complication. You can't predict the whole thing all at once. You could, but it probably wouldn't be particularly performant. So they kind of make it a little bit more like diffusion. So in diffusion, you add a bunch of noise to an image, and then you train a model to undo all of the different steps of the noising. In this, what they do is they break it up into a few chunks. So they say, make it 7 time steps and just guess some of the tokens at a time and do that progressively. And so with only 7 steps, they can say, okay, predict a few of these pixels and then a few of these pixels and then a few of these pixels. And so it kind of slowly fills in the blank. And we can see here at the first time step, it kind of took some guesses on some of the pixels, but a lot of them are pretty bad, and it's able to kind of iterate and eventually get to the point that it does like a real proper video that has everything filled in and it's pretty accurate. So this is kind of the like denoising masked approach where a lot of people previously had been doing things autoregressively. So instead of doing it sort of like many pixels randomly placed throughout time, they might do it just left to right, top to bottom. So you just say, guess the next token, guess the next token, and just kind of scan across and go down. And there's a lot of negative properties to that. Um, so
Sorry, before you move on, some of the earlier guesses, is it allowed to change them later, or once it guesses a particular token, then
it's able to continually change them.
yeah.
Yeah.
Okay.
And that was one of the experiments that they did was saying continuing to iterate was allowed. Yeah.
Okay. And then there's a question in the chat. Can you add an object into a video using this?
Yeah. Yeah, you can. So in theory, you just say give it a block, say this is the bounding box of where you want to fill something in. And then one of the other things that I didn't mention here is they also have a class token. So this class token could tell you generate a dog, generate a whatever, and it learns how to do this over time. And so what you could do is say, do this bounding box, fill it in, and do cat or do car or do whatever you want. Yeah, so that's another piece of the model. Um, and so I was mentioning the autoregressive approach. That's something that other people have done before, just basically saying start in the top left and just scan left to right and then go to the next frame and keep doing that. But the negative thing about that is you have to continuously guess again and again and again and again. Whereas the masked approach can kind of say like do a portion of it and then another portion and then another portion and it fills in the blanks. The autoregressive is way more steps when you're going further forward. So they show this kind of snarky graph where they show like, okay, when it's autoregressive and really small, it's not that much slower, but then it gets much slower as you go to bigger and bigger resolutions. And then once you get to 256 by 256, they just didn't even show it on the same graph. They're just like, yeah, it's way out there. So it takes 45 seconds to generate a video, whereas this takes 0.164 seconds. So they're just saying like, look, this is so much more efficient. And the same thing with diffusion. So they show diffusion is probably about 250 times slower because you have to say denoise, denoise, denoise 100 times or 1,000 times or whatever your forward steps is. And then this is the autoregressive approach, and they're saying this is 60 times slower. And then the MAGVIT approach of saying like fill in the mask instead of doing left to right is much, much faster. So this is cut off, but they were showing the speed estimates on different hardware. So they show that with the base model that they trained, they can get 37 frames per second. So that's, you can generate a video in real time, basically. You could just say, keep going forward. It's so fast that it will keep up. So that's all on the like inference speed side, but the other thing that we were interested in was the fidelity, the like it's producing realistic videos that look good. And so here's some metrics on that. So they had this Kinetics 600 data set. And they said, okay, just guess the next frame, guess frames into the future. How good is it at doing that? And here's all these different models that they compared against. And this is basically saying how good was it at actually predicting the next frame. And so you can see the video diffusion is actually pretty good. But then you compare it to the MAGVIT, and it has the advantage of being much faster when you're generating the video. And on top of it, when they scaled to their larger model, they got significantly better results. So it's kind of surprising that their jump from their base model, this B, to the L model, the large, got so much better. Like the jump from 24.5 to 9.9 is very significant considering they didn't actually change the size of the model. that much. It's like maybe 2 times bigger, but it reduced the loss a ton. Um, and then this is another table where they were comparing the various different methods of tokenizing and also doing things auto-regressively versus not auto-regressively. So all of these ones that are NAR are not auto-regressive, and this is auto-regressively. Um, so they were looking at this masked GIT approach, and what that was doing was the various different tokenizers and looking at 2D versus 3D. Um, and so you can see that their scores lower is better on this. So the MAGVIT scores significantly stronger and only takes 12 steps versus the autoregressive approach with the same tokenizer gets worse results and takes 1,000 steps. So scanning left to right, top to bottom, going frames forward is worse in terms of generation quality, and it takes 1,000 steps instead of 12. And then this comparing the 2D versus the 3D is interesting because the tokenizer is able to compress the information so much more efficiently. So we look at this 2D versus 3D step. The 2D gets a score of 222. This is saying only look at each image individually. And this is saying look at the like whole video sequence and compress that. And so you get a massive jump in performance just from switching the 2D to the 3D because it's able to compress it more efficiently. And this is looking at it in more detail, comparing the 2D and the 3D. And then they're also showing that starting from ImageNet significantly boosted their performance. So you can see there's a gap between the ones that they trained completely from scratch and the ones that they started with ImageNet and then expanded out. And then another piece to this was when they were training it, they could train it just for each of the tasks individually. So they could say only guess the next frame, or only guess the frames in between, or only expand it widthwise. And the performance of that was significantly worse than doing all of them all together. So this is showing their performance on each of the individual tasks, but then it's also showing what if we train it on all of the tasks simultaneously, and you can see across the board every single multitask is significantly better than the single tasks. Yeah, so training it on all of these different objectives at once made a better representation than training on just one of them, which is kind of surprising. You would think, okay, the frame prediction one should get better because it was trained only on frame prediction. And so this is the MAGVIT paper, but there's been a whole bunch of interesting innovation beyond that. This is one of the source papers, mask GIT. So this is a similar concept, but just for images. And then I wanted to point to some work from NVIDIA that's pretty interesting. So this is NVIDIA's take on this sort of video tokenizer. So they've just tackled that first portion of let's compress a video really well. And they're claiming that they're way better than all of the other ones, and they've trained it on more data, and they've got a better architecture and all of this stuff. So I just wanted to share this because I've been working with this a little bit, and it's kind of what's state of the art right now. It just came out a month ago or something like that. So they're comparing it against all of these other models. And if we compare it to like, this is MAGVIT2. So we were looking at MAGVIT1, VIT2 is significantly better, and then Cosmos is claiming to be even better than that, even at higher compression ratios. So this is saying reduce it by 8 on the time axis, 16 and 16 on the height and width, and it still beats the MAGVIT even at such a high compression ratio. And so they haven't shared that much information on their whole strategy. They don't have a paper for it. It's just this website, and you can go to their GitHub and download the model. But it's pretty impressive how much it can compress it and still look good. So this is comparing against the previous state-of-the-art Omni model, and this is Cosmos in comparison. So you can see the clarity is just so much higher um, with this model. So very, very impressive work.
Okay, question in the chat. Have you
Yeah.
checked out motion prompting?
No, I'm not aware of that.
There's a
Yeah, yeah, I'll check it out. Um, And last thing I'll leave you with is there's also this very good video that I've been showing to a bunch of people. So it's saying, why is diffusion better than autoregression? And it has some really good graphics of some of the stuff that I was talking about. And it's focused on diffusion, but the MAGVIT pattern follows something very similar. So I'll share this video in the chat too, and I recommend watching it if you're interested in this topic.
questions?
I have one. So, the video diffusion, completed the base model, right? Not the large model, the base model. It was the video diffusion, model particularly large, or like, how did it say, mention how the size compared to the base model, the large model?
I'm not sure. I didn't look that much at the video diffusion model. I would assume that they're similarly sized though. Yeah, I don't know the exact parameters of it, but the difference is really the mode. So I don't think that the size of the model was that big of a factor. It's just the number of forward steps that it's doing. You might be able to get a better video diffusion model if you just said scale it up to the size of the large, but you're paying the cost of that 1,000 times or however many diffusion steps you take. So scaling up is much worse for diffusion than it is for this method because you say 12 steps versus 1,000 steps. If you make it 30% slower, you're feeling that 30% 1,000 times, for example.
So diffusion is just, a video diffusion model would be a lot, slower.
Yeah. Yeah.
Or-
Yeah. Yeah. So I've been playing with both of these methods on some satellite forecasting stuff. So the goal is basically we have a bunch of videos, satellite imagery of the cloud's movement, and then we're trying to forecast where's the cloud going to move, how is the temperature going to change, and stuff like that. And so I've been playing with diffusion, and I've just started playing with this tokenizing stuff. And it's very difficult to train the diffusion models. It's just expensive to run. And then I go, okay, I'm going to run predictions on 300 sequences of 24 frames. And then it takes me 8 hours, even with 3 GPUs. So that's part of my motivation for looking at this approach instead, because it's so much faster while also maybe getting better forecasting performance. Yeah.
But, think about training on multitasks being better than single task. Have we seen that anywhere else? Like in some other model? Or is that unique to this?
I think that that's probably not super unexpected. I think there are some language model papers that have shown the same thing. I don't remember them off the top of my head, but I know that there were some papers where they just basically said like, there's one style of model where you say fill in the blanks, and one model where you say guess the next token, and one model where you say, and I think it's been shown that doing all of the variety of tasks is helpful. But for simplicity's sake, I think for like in the text field, everyone has just defaulted to guess the next token, and that's been good enough for now. But yeah, I think often the multitask approach helps generalize because you're teaching it more about one task might be focusing on the tokens next to it, and one task might be focused on going forward in time, and understanding all of the different kinds of relationships probably helps there. Yeah.
Yeah, it's not completely analogous because it's not tokens, but just in like older computer vision, if you have a model that's like a CNN and you have it do classification, then if you also have it predict depth and you also have it predict segmentation, you get a better classifier. So I guess it just helps it tease out real relationships from spurious correlations.
Yeah, okay, that makes sense.
But again, not quite analogous because that's not tokens, but I think it's a similar phenomenon. Another question in the chat, I missed it. Okay. All right.
I have a question regarding the image net, like, so where does it like factor into the architecture? Like, you said like training from scratch is like image net, it's better, so where does it like come into picture, like which component?
In the tokenizer, they're doing some CNN,
Okay.
and that CNN can start from random weights, or it can start from something that was trained on ImageNet. And so they can plug in that CNN at the beginning that's encoding, and then that's how they inject those weights.
And another question I had was like regarding tokens. So we said like you go from your image resolution, you downsample your image resolution by 8 by 8, and then your time steps by 4. So let's say I have like a 128 cross 128 image and 16 frames. So then do I have like 4 tokens of 16 cross 16 resolution, or like, is that correct?
Yeah.
Oh.
Yeah, exactly.
All right, last questions from the chat. How do you determine how long video you're gonna generate?
You can change that just based on how many you generate. So you can they have a good video. I'll share my screen again for a second. They have a good video in here. Let me see if I can find it.
I think basically it's how many temporal masks you
Yeah.
stick on the end, and it'll fill in all masks. So if you stick a few, you only get a couple frames. If you stick a whole bunch, then you can ask for a lot of frames.
Well, I mean, it's taught in this certain grid though. So like in this that I'm showing here, they said basically give it this tall, skinny video and then run out painting and slide it over, run out painting, run out painting. And you can do the same things in the temporal aspect. So you can say just scoot it forward, scoot it forward. So you can generate as long of a video as you want. It's not guaranteed that it will be coherent past a certain length. So like this is a future prediction thing where they're saying give it 1 frame and then guess forward. There's no guarantee that it keeps being a useful video, but you can keep extending it as long as you want, basically.
Thanks.
I'm gonna unmute. All right, cool. So tons and tons of stuff with language models. So we're kind of sticking with a computer vision theme today. Let me share my screen. And sec. All right. So today I wanted to talk about segment anything. So there's segment anything, and now there's a couple months ago SAM2. And what you'll see is there's some common themes. Segment anything was last year, so I think possibly some of the things that Ryan talked about could be taken advantage of to maybe re-architect the way it works and have it work even better. So just briefly, segment anything, traditionally image segmentation, right? So what we're saying is give me a picture and identify all the pixels that are associated. And if you're just doing like simple instance segmentation, then typically what you do is you define upfront what classes you care about. So let's say you care about people, cars, and dogs. It's going to tell you what pixels are part of people, what pixels are part of cars, and then every other pixel is just background. Doesn't matter what class it is. Okay. So last year, when Meta came out with Segment Anything, they said they wanted to create a foundation model. So the same way with language models, you have this super powerful general purpose language model, and then you can adapt it to say, I want to do sentiment, or I want to do this, or I want to do that. Okay. So they wanted a foundation model for segmentation. And so the idea was we're not going to have it trained on specific classes. We're not going to train it on dogs or people or whatever. We just want it to get the general intuition of what is a thing. Well, no matter what you're looking at, just what's a thing, okay? And so it basically had to sort of learn what object boundaries are. And interestingly enough, in the original Segment Anything paper, they said you have to start out by having humans like annotate ground truth labels, right? They said they purposefully gave the people no instructions, no clear instructions. They're just like, do the boundaries on things. Anything that you think is a thing, just do that, okay? And they purposefully wanted to just say like, you're a person, you have experience in the world. If this is an orange and that's an apple, they're separate things. You wouldn't just combine them, you know? So I thought that was kind of interesting. And then ultimately, later on, they had to actually push and to try and get like good diversity and try to really make sure like they, understood what exactly does the thing mean or whatever. So I'll go through a little bit of Segment Anything, and then SAM 2, they kept most of the architecture, but what they did is they extended it from just images to now that they could run on videos. And if you have say a soccer ball in frame 1, then they'll track that soccer ball throughout the rest of the video. So they're going to introduce this memory concept. But what you can see is because it was built on SAM 1, it has these image roots. So I think what's interesting is Ryan was talking about a 3D encoder, but SAM 2, even though it's doing videos, is still just using an image-based encoder. And so that, I think, might be a leap that we see in the next generation of things. So here's just a visual example of the difference between classic old-fashioned computer vision segmentation. Okay, so here's an image, and I say person, dogs, and cars, and you just get 2 masks. So here there's an outline just so it's easier for you to see, but it's every single pixel inside the purple outline is part of that one object, and then every one of the yellow pixels is an object. Whereas Segment Anything, given this very busy image, would have hundreds of different masks. And it's a little easier if you see sort of like the original image and the mask side by side, but just for space, I just am showing you only the mask ones. So you have to just sort of infer like, oh, okay, like there's a little bit of a purple over this guy's face. So like the whole face is one object and blah, 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 blah. But sometimes it's a little hard to tell when the overlay colors are kind of faint. It's not exactly clear, but you can see here there's something like 350 different objects that it identified. And if you look closely, it didn't necessarily identify every single object. You'll be able to find examples where there's pixels that didn't get picked up by anything. All right, so how does it do this? So first they had to come up with this idea that we are going to turn this into a prompted task. So we're going to have a prompt, and then we're going to have images. So the prompt encoder can accept basically a point or a rectangle, and it also would accept, because of the way in which you can sort of like improve upon things, it'll accept a mask. So you could say, here's a bunch of pixels, and it's not necessarily the complete object. So just potentially add on to these pixels, okay? And then also SAM1 had text. I'm not going to talk about that too much. They ended up dropping it. It was fun, but it didn't work super well. So then they have the image encoder that creates an image embedding. And so those two things sort of happen separately. And then how they get combined is on the right, you have this mask decoder, which basically says, for one prompt, let me look at the image, let me look at the prompt, which could be, again, a collection of things. So it could be multiple points, masks, rectangles, whatever. And if those are all one object, then it's going to try to find what object matches the union of all of these prompts together. Okay, so if you had a dog and a car and a person in an image, you'd have to give it 3 prompts. Okay, and it's going to actually iterate over those. A little more detail about what the one other thing. So there's this idea that if I just give it a point, so if you look at the left-hand column, is this an ostrich, an emu? I don't know. If you just clicked right here on the head, did you want the whole bird? Did you want the body? Did you want just the head? And theoretically, you can have quite a few levels, but what they found was that generally speaking, 3 levels was enough. Okay, so on the far right column, you have like some company's front lobby. So when you click here, are you talking about the whole wall? That would be the biggest thing. Or are you talking about like just the word Zurich there? Or did you really mean the Z? You were clicking on the Z. You didn't click on the other letters, right? So so the way that segment anything works is it actually outputs 3 predictions for every prompt that you give it. And the idea is that it would learn to output a whole object as big as it can sort of see, a part of that corresponds to what you prompted, and then maybe a subpart that's like even smaller. Okay. It doesn't always do it perfectly, but then what you could do is, let's say, it didn't give you the option for the whole wall. It only gave you like Z, Zurich, and Zurich with the little circle logo above it. You can just simply add a second point to the prompt that's on the plain wall, and then it would be forced to say, well, how can I union that with just this, what is it, tan color? And then it would probably say, oh, so then you must mean this whole wall. Okay. So generally speaking, it does pretty well for like everyday objects. So if you give it an everyday picture, it's going to know the difference between like shirt and pants, and the difference between an apple and an orange, or whatever. If you give it a biology slide with like water from a pond, and there's little whatever unicellular organisms floating around in there, it's going to pick each of them out, right? But if you give it something super complex like a chest X-ray, then that's not necessarily something that it's well trained, that it knows how to do. All right, so then now getting a little bit more detail in the architecture. They don't have tons of details in the paper. I'm going to focus more on sort of the high level concept than the gory details. So for the image encoder, they are starting with something pretty much off the shelf. Okay, so this is not something that they had to completely redesign from scratch. Segment anything 1, they use a mask autoencoder. And the idea is very similar to what Ryan talked about, but it's just 2-dimensional. Okay, so for images, you punch, you patchify, you punch holes into the image, and you have it predict those missing holes. And you do this at random so that it can predict a hole that's missing in the middle, on the edge, in the corner, pretty much anywhere. And so this gives you a just very good bottleneck embedding representation for any image. This is the most expensive part of segment anything, is coming up with a really, really good representation. So it's important that even though I said if you wanted those 3 objects, you would run it 3 times, that image I showed you that was really busy, you're actually running it hundreds or thousands of times. So you only do this once. You encode the image, and then that sequence of tokens gets used over and over and over and over and over again. The prompt encoder is pretty light. So basically, they learn an embedding for each prompt type. So there's just a code for point, there's a code for rectangle, there's a code for text in the original model. They did also do something with masks where they have a CNN that just sort of spatially, shows where it is. And then you also have to have positional embeddings. So pretty much anytime you have anything with attention, you have positional embeddings. So for a point, it's basically like your positional embeddings are the real data, not the whatever. So in that sense, they didn't have to do a lot of work for these prompts. They just had to have the model learn how does it want to represent the notion of a point, the notion of a rectangle, which is 2 points. And then the decoder was the part that really surprised me, that it's really pretty darn small. So in the end, they had just 2 layers. So like if you look like whatever, like GPT-2 small is 6 layers, I think. And then a lot of these models today are 48, 60, whatever. These language models are much, much bigger. So this is just 2 layers. These layers are a little bit heavier weight, okay? So what it does is it has the prompt go through self-attention. And this is, just like Ryan was saying with MAGVIT, I believe all of these are BERT style. And so there's no causal attention. So every token can kind of attend to every other token, update the prompt. Then you have cross attention where the prompt is looking at the image and only the prompt changes, and then where the image is looking at the prompt and only the image changes. You do those 3, and you just do that twice. And that's enough to then basically have an MLP and prediction head that outputs a vote for every single pixel to say whether or not that pixel is part of this particular prompt. And then you have 3 attention. Then you have 3 prediction heads because you're doing 3 things. And that's really like the design of this segment anything. So in SAM2, they wanted to be able to support videos, so they had to make a few changes. The first change they made, I don't think was because of the video, but they just said, there's a better model. This higher model is like VIT, except it's specifically got a pyramid structure. So you see in a lot of computer vision, this pyramid structure where you have explicit pooling. And so basically you have low-level resolutions early on, and then as you get later, you have high level that has a much larger focal width. And so the idea here is then you get outputs from the different layers. And so it's this idea of multi-scale features. Hold on one second. I saw, I don't know where my menus are. Yeah. So yes, so the image encoder was originally a VIT, and VIT has positional embeddings for the patches. And then Hyra is the same, except I think they just have very explicit pooling, and then they draw outputs from the different layers to get this multi-scale features. So they wanted these features so that you can sort of understand small objects as well as large objects. So what if you gave it an image instead of having 300 objects? There's just one big picture of your dog. You know, you don't want it to say, well, I can't really do a mask that's bigger than like a little corner. You want it to be able to say, yes, I can just say 3/4 of this image pixels are all dog. They introduced this new attention layer that they called memory attention. And basically what it does is it has the image that you're currently working on, which is just like original SAM1. And then it also does cross attention to this memory bank that has information from other frames that we'll get to on the next slide. The prompt encoder is basically the same. They got rid of text. The mask decoder is largely the same. The main difference, though, is now that they have 2 inputs. They're going to get an input directly from the image, just like SAM. But now they're also getting an input from the memory attention, which means that it's the frame context aware information as well as just this one. So if you give it a couple prompts on the first frame of a video, then basically the memory is empty. And so then it's kind of just like SAM1, okay? But once you start having multiple frames where you've prompted or multiple frames where you've already done predictions, then it can say, well, if the if the soccer ball was here in these similar spots in the last 3 frames, it gives me a huge head start as to predicting where the soccer ball is going to be in this. And then one thing I hadn't thought of is now once they extended to video, they wanted to have this concept of there's an object, but it got occluded even though it's still in the conceptual frame, but you can't see it. And so they added an additional binary head that basically just says, I don't want you to forget about this object, but we're not going to make any, there's no mask for this object in this frame because you just can't see it temporarily. And so then because it's a temporary thing, it then means that later frames won't just forget about the object. Later frames will say like, you have no location information for me, but I know that that object is sort of still conceptually around. All right. So with a little, now let's get into this new memory concept. This was not necessarily the most fancy thing that they built or whatever. So they have a memory encoder, and what it does is it takes your predictions and it downsamples them. And then it takes those and it sums it with your image embedding. And they said, I don't really know what this means. I haven't, the model's publicly available. So like if I really wanted to, I could just look at the architecture, but they say some lightweight convolutional layers. So that's not the focus. So mostly it's just scale down my masks and slap it on top of the image, and that's what I'm going to store in the memory. In the memory bank, they have, as far as I can tell, 3 slots. They have a queue for some number of recent frames. And this has the spatial information as well as the temporal information. So this was 1 frame ago, this was 2 frames ago, this was 3 frames ago. They have a separate queue, which is all the frames where you've prompted it. So this means that you have ground truth information, and so it's like kind of important. If you do the typical thing where you only label the first frame and then you just want it, then even though that first queue, if it's like, say, size 8, when you get to the 10th frame, the first frame is going to be gone. But your prompt frame is in a completely separate queue and will never be lost. Okay. And so the only way in which you would lose one is if you had more frames in which you did prompts than whatever that queue length is, then at some point the older one's going to fall off and you're only going to have the newest ones. And then I don't know the details, but they said they basically have some vectors that they store for the predictions. So I think it's mostly just about where was the ball on frame 2, where was the ball on frame 3. And so you can see sort of this pipeline down at the bottom where, again, you put an image in, it encodes the image. There's a tension that combines this image with the memory, if any. And then you run your typical SAM1 sort of decoding with the prompt information, and you get a new information with mask information. So then what you're going to do is you're going to store this image and mask information in the memory bank so that future frames can reference it. And again, it's all still pretty lightweight. They made some other tweaks, so they said that now SAM2 runs like 6 times faster than SAM1. And that's basically the gist of it. So when you're doing a video, it's very important that you process the frames in sequential order. Okay, you don't just like randomly do frame 1, then 21, then whatever. Because of this memory bank thing, you want it to have the most recent frames. One of the interesting things, it took me a little while to test this to make sure that it really did work that way, is they process the frames sequentially both forwards and backwards in time. So if you prompted only the last frame of a video and said, here's where the soccer ball is, then basically going forwards in time, they can't do anything. But going backwards in time, they basically can then say, so then in the second to last frame, this is where the soccer ball is. And then in the third to last frame. And in one of the demos on their website, you actually will see sort of like, at the bottom, you have sort of the video reel. You'll actually see the pointer go this way, and then you'll see it go that way. So it's like thinking, and you'll see it go this way, and thinking, and then you get your whole video with all the predictions. All right, so a little bit about the data and training. One of the things that's interesting is whenever you read a paper and they're trying to do something that's a frontier type model that's going to be better than anything else out there, okay, you have this problem that you don't have the data and you don't have anything pre-trained that's going to help you, right? So there's this wonderful cheat that if like you wanted to build a special purpose um, LLM for your company or whatever, even if you were going to kind of build it from scratch, you still can do things like use GPT-4 as a judge, use GPT-4 to pseudo-label your data, da, 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 da. But when you're building GPT-4 and it is supposed to be the best model out there, you have no judge that's better that can actually do this for you, right? So it's the same thing with SAM. When they came out with SAM, they didn't have anything to help them. When they built SAM 2, they didn't have anything to help them with video. So what you see is this active learning process in most of these papers where somebody's trying to build what they consider to be really at the frontier. So we label a small amount of data. It takes a lot of humans. It takes a long time. It's really slow. And it's a small data set. And then we train the first version of our model. And the model's not very good, but now we can use that model to pseudo-label things. And now our human annotators can go a little bit faster because it's actually sort of working. And then we use that larger data set because it went much faster to label things. And then we'll get a model. And then the model quality tends to like not just go linear, but you know, as your data grows, it tends to get even better. And so then you get to a point where you're sort of like, yeah, the model's just auto-labeling everything and we're just doing minor corrections. And so now the amount of data we have has exploded tenfold, and then we train it on all of that. So saw it in both of these papers. I'm trying to remember what other papers, but I've definitely seen it where, again, if you see somebody who's saying like, oh, we're this upstart, we're going to make this 3 billion LLM, generally you'll see in there somewhere they're going to say they use GPT-4 to help them in the process. But when you're doing this, you can't, you have to bootstrap yourself with this active learning stuff. So at my company, that's one of the things that we're looking at is whether or not we want to do some type of active learning with our data in order to try to get a better model and also speed up the process versus just saying like, oh, we'll annotate a mountain of data all in and just do it all in one pass. Yeah, so I thought that was interesting. And like I said, I've seen in other papers, I just can't really remember exactly where. All right, so a few other details. So this idea of I want to segment everything. Well, okay, I gave you this really busy image. It's got 300 objects. How do you know like what to segment? I said that you have to prompt every object individually. So basically what they do is they just create a grid of point prompts. And if it's a not very busy image, you can get away with maybe like an 8x8 grid of points. A super busy image like that, you would have needed way more than that. I don't know, you know, what they would have done, like a 256 by 256 grid. And then you just, again, you encode the image once, but you got to run that decoder over and over and over and over and over and over and over again with all these different prompts. And then eventually, some of the larger objects are going to get multiple grid points. And so then you deduplicate the answers. And that's a pretty standard thing if you're familiar with like object detection. You run non-maximum suppression and you just sort of deduplicate based on IOU or something like that. Yeah, and so I just want to clarify, you can specify multiple prompts per object, and they also have the idea of negative prompts. So if you clicked on a person and you got the whole person, but you're like, no, I really just wanted the shirt, then you can actually do a negative prompt on the pants and a negative prompt on the head. And then that'll force the model to do that. The masks the outputs do not need to be contiguous. It's predicting every pixel in parallel. Largely, you tend to get this notion of contiguous objects just based on its inductive bias. But I'll show you an example, and clearly they don't need to be contiguous. So then I mentioned videos backwards and forwards, and then Sam one came out a little, year and a half ago or something like that. So there's been a gazillion papers. There's no way I could possibly read them all, but there's been a lot of people who've looked at what Sam's good at, what it's not good at, how can we extend it, how can we whatever. One thing I'll mention is there's a recent paper called Samurai, where they said Sam 2, the memory bank, it's kind of dumb. Like it's just kind of like here's a few recent frames, whatever. And so what they did instead of having these object pointers, they said, what do we do when we want to track objects? The simplest thing is a linear Kalman filter. So let's just actually run a Kalman filter on every object. And so what they found is if you look at some of the SAM samples, you'll have, say, some objects on a table and they're not moving. And then when your hands move, it blocks them, but the objects haven't moved in the meantime. But if you have something else, like a guy on a bicycle and a bus drives by and the guy's moved quite a bit since, then that's the kind of thing that SAM2 would do poorly on. It wouldn't figure out that's the same person. And so there's various things, but Samurai is the one that just recently I saw was getting some attention because they say it does a much better job of tracking the same object, which ultimately, for people who are doing this, that's what you want, is you want to basically annotate frame one and say, I care about this bicycle, I care about this person, I care about this ball, I care about this dog. Now, for this 30-second video, just track all of these objects, and you don't want to have to go in at the 8-second mark and clean it up and say, you missed the bicycle. Now I got to tell you the bicycle's here. You'd like it to just get it right in one shot. All right, so I'll flip to the demo, but basically, SAM 1 and SAM 2 pretty much have been very notable events in terms of like computer vision. And you can do very good zero shot work. You don't have to fine tune or anything. You just take it right out of the box. And again, like I wouldn't necessarily use it for X-rays or expect it to do that kind of a thing. But like my company, we do like security videos. And so it is sort of everyday scenes and it knows what people are, dogs are, trees, sidewalks, all those things. I noticed that it does seem to pay attention to color. That's a pretty darn good cue that if your shirt's gray and your jeans are blue, like where does the shirt end? Where does the jeans begin? That's a pretty darn good clue. But it is definitely doing more than just color by numbers and dividing it up into color regions. It definitely has a sense of what objects are. And then when you run it, I don't know that you can do this on the website, but when you actually download the model and run it, there are some parameters that let you tune whether you want big objects or whether you want little objects. So like I ran it on a picture of a house, and like if you tune it one way, then you click on the house and you just get, we do the full grid thing. You just get one mask for the whole house. And if you tune the parameter the other way, then it's like the main wall, door, window, shutters, or even if the windows have the whatever those things are called, the little piece of wood in between, you get 4 panes and the wood in between. Like, so depending on how you tune the knob, or even you'll get like the door is an object and the doorknob is a separate object, which again, if it's a different color, it's pretty easy for it to pick it out. If you have things like a sidewalk and in one place there's like a hole in it, right? Oftentimes I'll notice that the mask will be missing the hole because the hole's like black, but the rest of the sidewalk is white. If you have a lawn and there's just like brown leaves that have like blown around, but they tend to like get piled up near like edges of the wall or this or that, then sort of like the lawn mask will end before the leaves and the wall mask will be above, but there'll be just sort of this no man's land in between where it's like nothing. So, there's some details like you wouldn't necessarily want this for your life depends on it, accurate to the pixel masks. But really cool model. And then the crazy thing is LLMs have distorted our notion of what's big and what's small. And so they have I forget what they call it, but the tiny model is 39 million parameters, and the large is 224 million. And these days it's like, oh, the new small llama is 8 billion, and this is 200 million. Um, and so it's like 200 million. If you have a consumer, like you don't even need a 4090. You can run it on whatever the lowest end one is. What is it? 40, 60, 40, whatever. I don't know. But like it's that. It's that small. LLMs have just completely distorted our notion of what is bigger. My experience is that actually the difference in quality between the tiny and the large is not that big. So if you have relatively easy things, so if you just said like, here are my pictures I took on vacation and I want to segment them for some reason, you probably could use the tiny and you wouldn't really notice the difference between that and the large. It's only if you have like sort of hard problems. So the reality is then you could be using this less than 40 million parameter model. You might be able to get away with that. Like, I don't know if you can do that on a phone, maybe. So pretty impressive. Yeah, so in terms of the theme, how do you build one of these things? Well, you need some attention layers that you just say, what do I have? I have prompts and I have memories and I have images. Let's just build some attention between them. And I mean, sure, it took more work than that, but basically we do that and it works. All right. So you guys want to see Sam? So here's one of the demos on their website. And sorry, I have this box. There's something, I don't know, going on, some alert on my screen. So we have this video. If I just, can I play the video? So you'll see that this guy's like moving around these little kids' toy blocks. Okay. So what I'll do is at the start of it, let's say I'll pick this block because his hand's going to cover it at some point. Okay. Or I have to figure out what this. Oh, yeah. Sorry, guys. Oh, which window it is. Is it this one? No. Some window is messing me up here. But I can move it. That's convenient. All right, let's try this again. Just start over. All right, so I'll pick this object, and then I'm going to say add another object, and I'm going to see these fingers don't all touch each other, but I'm going to pick one. And you see how even though it's not a contiguous object, it picked out the four of them. And then I'm going to add another object and maybe try, like, actually, let's do this block, which you can't even see at the beginning. Okay, so I've got three objects, the blue, the yellow, and the green object is already hidden right now. I'm going to say track objects. I think this is going to run a little faster than real because they've pre-cached the image encoding for this. Makes for a better demo. So you can see like this green object keeps getting covered up, and then even though I guess maybe, but yeah, so like there it got completely covered up a couple times, but it kept track of where it was. And then oops, it goofed. At some point it went from one hand to two hands. Okay. So what I can do is I can say I want to edit object 2. And I'm going to say not this hand. just the other one. And you'll notice that down below it says I've made annotations on frame 1 and now on whatever this frame is over here. So if I say track objects now, it reruns. It does not run this fast when it's not the demo. But I've rerun and it should do a better job of only doing the one hand. Oh, I guess at one point the two hands touch,
Yeah.
and that's where it gets yeah. So then I could theoretically I could go to the point wherever it is where the two hands touch. Is it here? I don't remember. Yeah, and so I could add another negative here if I need to clean it. Right. So your goal is you wanted to get it completely right all in one shot, but you can see where generally speaking, it's doing what it's doing. And if you look down here at these blue, yellow, and green lines, you'll notice there's parts where it's like faded out. That's actually the frames where the object's occluded. So that's that extra prediction head we talked about, where it said you cannot see this object at all. So there's 0 mask pixels associated with these frames. And so I wanted to pick like this green block because you see at the beginning, towards the beginning of the video, there's quite a few times when you just cannot see the block at all. Some question in the chat. Oh, thanks. Yeah, and so there's a few different, I don't know, there's a few different videos on the demo, and now when I first started playing with it, it wasn't Hugging Face yet. It was kind of a pain in the neck to install, but now it's on Hugging Face, so it's just a few clicks. And like I said, there are settings for how aggressively you want it to combine things. So like I had a picture of a house and there's these little round bushes in front of the house. And on one setting, it just said, here's one mask for bushes, all of the ones in front of the house. And then at the other extreme, it was bush 1, bush 2, bush 3, bush 4, bush 5. So that is something that you do have a level of control. If you have a super busy object, a super busy picture, instead of doing a crazy high number of grid points, you can get better performance. They let you do hierarchical grids. And so basically it'll, I don't know the details, I haven't played with it, but it'll basically subdivide and it'll do a subgrid on a little patch. But I'm assuming that then ultimately at some point it has to like do 2 different passes of NMS or something like that. But so there's things, and that stuff is all sort of pre-built in order to do it. And if you use the model, then obviously you can get all the masks out individually and stuff. And this is a really old notebook, so I'm not going to share it because it's before it was on Hugging Face. But you can see here where I did different predictions. So this one has a lot of little objects. And then I think I have this one where I flipped the setting in. So you can see there's many fewer, just the entire house was one mask and whatnot. And there's different ones where basically it would predict like lawn. And even though the 2 sides of the lawn were split by sidewalk, it would say, but conceptually, I know this is one lawn. And then for the output, you can see here, like, here's object 1 mask, here's object 2, object 3, whatever. And on this one, I think you see there's a few pixels like right over here. So if you wanted, you could do your own like dilation erosion or whatever and just sort of clean up if you don't want to have tiny little holes in your masks and or speckles of additional pixels. That's like a very easy thing you can do computer vision to get more whatever convex solidly filled masks. So when I was experimenting with it, that's what I did. I did a little bit of dilation and erosion, and just then I had what you and I would tend to think of as like just big contiguous solid filled masks. All right. So yeah, so that's that's Sam too. Any questions?
Like, where do you use the and like at what point of the model do you use the occlusion score or what?
It's just a so there's three prediction heads for every prompt. Okay, the prompt can be again a set of unlimited length, and so it's predicting every pixel and just yes, no, is it occluded? Okay, so it's just like an additional output. Yeah. That's question is about how it does with light changes. I I think that you definitely can run into issues. Okay, so if you had your lawn, but there's like a shadow, so part of the lawn is bright green, the other part is dark. Okay, for sure, if you have the setting set cranked to give me small objects, it's going to split it right there. Okay, it's going to give you the light green part and the dark green part as separate objects. You can manually merge them, but you would have to go in and you would have to adjust that. I think that I have seen things where it's more gradual and it has some sort of it does have contextual information, so it does kind of understand the idea of a lawn or whatever. But like there was this driveway and it was made of like big square cement sections or whatever. And under most settings, what it tended to do was just give me a whole bunch of squares. And it didn't just say, this is a driveway, you know. And so I was like, I don't really want, whatever, 40 masks. I just want one big one, right? So yeah, so it's exactly stuff like that. And again, especially light and dark and different colors. So if you see someone in an outfit and they have a belt and a belt buckle, it's going to tend to say that the shirt's an object, the pants an object, the belt's an object, and the belt buckle, because it's a different color, will tend to be a fourth object. But if you do tune the knob, then it'll just say person. Yeah. In the chat, yeah, can you use this for object detection? Absolutely. So basically, segmentation is usually more specific than object detection. So you can just do a bounding box around whatever the segmentation mask tells you. And in fact, I'm talking to companies that do annotation, and it's debatable whether or not experienced annotators, it's faster or slower. But about 2/3 of them now have segment anything as just an option in their user interface. And so basically, if you need to do a bounding box on a person, they can just click on the person, segment anything, will just say, here's the person, and or they'll then turn it into a bounding box. But if you're a really good annotator, it might be actually faster for you to draw the bounding box with the drag than to click and then have to edit it. So it's debatable, but if it's just like you or me, we're inexperienced at annotation, it's probably a lot. It's very convenient and a lot faster. What happens when the objects morph? So it's certainly the case that like if the dog is running, the legs are moving. They're not like in the same position, and it doesn't seem to really have a problem with things like that. But I would imagine that there's limits to how much change it really can handle. This tab has a bunch of different samples that, as you just sort of scroll through, I'm trying to see if there's one where things change too much. Most of these are things that are moving, but not really. Like the ping pong paddle is definitely, when it's edge on, is quite a bit different than when it's face on. But the colors kind of staying the same, the locations kind of staying the same. So I wouldn't say it's really that hard of of a task. And then, yeah, this silly thing they have with the starburst thing. They actually do have that in the model where basically it's like um it'll find the center of mass of whatever your mask is, and so then it can do video effects based on like where that center of mass is. So it's like because I really need that starburst effects in my videos. All right, cool. We're at 1:30. We're at time. Any other questions before we wrap here?
Um, what's your experience with temporal?
Can you apply SAM to like grainy security videos?
Yeah. So the question, if you guys couldn't hear, is does temporal information help with classification? So what I can tell you is I did an experiment with a dark video, and it's just a street scene. Okay. And when I asked Sam to segment the sidewalk because there were like cracks and like dirtier spots and whatever, it had a hard time saying that this rectangular region, and it's whatever trapezoidal perspective, but that this is the sidewalk. It would miss little bits here and there and whatnot. And actually, what you saw is after it processed the first frame, when it did the video, it tended to actually improve the original frame's mask slightly. Okay, there's times where it would miss a certain section that was maybe a little dirtier and it thought it might have been a separate object. And then like upon doing the temporal on both sides, it's like, oh, well, I guess it really is part of the same object, so I'm just going to include it. So that's where, remember the memory attention, which is sort of like not just looking at the object, but then looking at the things, the frames that were around it, it gave it a slight boost. I think to a large extent, we haven't seen the degree to which people have taken advantage of the temporal information, just because these models tend to get a lot bigger once you give them video. And so just not that many people have done it. But absolutely, if you said like, I'm trying to think of one of the things that I do at work all the time is here's this small object inside of a picture. Okay, it's a little black smudge. Is that a black dog, a person that you just can't see very well, or a shadow? A lot of times I could ask 10 people and we still have no idea. If you watch the video and you see the temporal context, it's like everybody's like within a quarter second, like, oh, it's a dog. Oh, it's a shadow. Oh, it's a person. So it's very clear to me that there's tons of information there, if that you can gain from the object moving or the lack of the object moving. It's like, well, if that were a dog, it's standing awfully still for 10 seconds. It's probably a shadow, not a dog. You know, it's probably just that tree branch has a shadow that looks very dog shaped, right? Like the man in the moon, the face on the craters of the moon or Mars or whatever, right? So yeah, I think that is an opportunity, but we haven't yet seen too many people take advantage of it because the data volume tends to blow up when you go to video. Anything else?
You mentioned about the grade for property. I didn't get that part, like the grade for points. I didn't.
The original grid, or when I was talking about like subgrids?
Not sure. Like
Okay. Yeah. Yeah. So I was showing in the slides. Here's on the right a scene that segment anything identified all of these. How did it identify all these? It didn't magically know to segment. What it did is they just slapped down, let's say, a grid of 64 points by 64 points. And it said for every one of these, make a prediction what object it belongs to. And then so like, see, this car is actually pretty big, or this guy and his jacket is pretty big. there would be multiple points that would correspond to that. And then they would just deduplicate it and say, oh, well, we have 16 copies of the shirt and we have 400 copies of the car. And so we're just going to keep only one. And so then you end up with one of those. But that's how you can get all these small objects. If I did a 16 by 16 grid, then you would see like this object and then the 1 3 over and then what you would actually see the grid because you would see these are where it found objects and in between it was all considered background. I don't know. I mean, for me, I've only just done it manually. So you can take this image and you can just say, do a 4 by 4 grid and you're going to only find 16 objects. And you say, do a 64 by 64, and then you're going to find a gazillion objects. And it's impressive to me that they were able to make the decoder that lightweight, just 2 layers, because they knew that somebody was going to run it 2,000 times on an image, and it could not be this really big monster heavyweight model, because then it really would be pretty slow when you run it 2,000 times. Yeah. So that's the other thing is like if you have proposals, then you can, instead of using a full grid, you can just somehow use those proposals as your starting points. All right, cool. Thanks everyone. Thanks for everybody who's joining us online. And we'll wrap things up here. Brief note, next week is the book club, the 2nd chapter. So that's analytic geometry. We'll be here, same place. Ryan will be leading that discussion. And then we're not currently planning to do any more events until January. So we'll be off for the holidays and then probably the first Saturday in January, but depending on schedules, if anybody has conflicts, we might push it. It's normally the first Saturday, but we might push it. So the first Saturday, I think, is like January 3rd or whatever. It's still a little bit early. But I'll get those posted up on it. All right. Thanks, everyone. Bye-bye.